Dr. Jigu Sampo, Tomohiro Kawabe, and Professor Hirokazu Kobayashi. And the title of talk is Isolation of Phase Object in Enhanced Microscopy with Q-plate under tilted laser illumination. Please start your presentation.
Hello everyone. Okay, as you can see the title of my conference paper on the screen, Isolation of Phase Object in Edge Enhanced Microscopy with Q-plate under tilted laser illumination. So let me introduce myself. My name is Jigmi Zangpo from Kochi University of Technology and my home country is Bhutan. So without much ado, let me start my presentation straight away. So first let's look at the introduction of microscopy. So we know that microscopy is an important tool where it is used to magnify the tiny object. So it is being used in various fields. The important application could be in biological imaging and medical examination. Now there are various type of microscope. So out of which I'm going to focus on two type. The first, the traditional bright field microscope, which, which is used to visualize oblique amplitude object, so AO, which is shown out here. So here it is a phase object which that bright field microscope visualize that object, which is not clearly visible. So therefore, such type of microscope has a disadvantage where it cannot observe the transparent phase object. Now we have our the differential interference contrast microscope, which is also called as DIC, so which is shown out here. So the same phase object has been observed using DIC. So the lower part, the edge is brighter compared to the upper part, so which clearly shows that the object has been enhanced in the vertical section. So therefore, such type of microscope, that DIC, can visualize the face object, but it has a limitation where it can enhance the edge in one direction. Now we know that typical bright field microscope could view the amplitude object only. Now if we want to enhance the edge of this enlarged amplitude object, so we need some imaging processing software. So such type of system take longer duration. Now we have the hardware system where we have 4F system, which is added to existing typical bright field microscope. So we have the filter, which is known as optical vortex mask. So such type of system, which is called as optical vortex microscope, is capable of enhancing both amplitude object and phase object. Now suppose we have object out here f in xy. So this object is sent through this system, so optical vortex microscope, and we have our output where each of the object has been enhanced using such system. So this system, optical vortex microscope, can enhance the edge in all direction, unlike the DIC, which could enhance the edge in only one direction. So how this edge has been enhanced? So this output f out is given by inverse Fourier transform of the Fourier transform of this object multiplied with the filter function, that is exponential I theta, which is basically the object is being convolved with the convolution kernel, that is Fourier inverse Fourier transform of exponential I theta, which will dictate the edge due to difference in intensity and phase. Now in our experimental setup, so we have used Q-plate as our optical vortex mask. So this is a Q-plate where we have used pi retardants and one topological charge. So each line represents the spatially variant phase axis at each position. So unlike other type of optical vortex, Q-plate is polarization input dependent. So depending on the input of polarized light, so it will give an output. Suppose if we have light, left circularly polarized light as an input light, so with the help of this Q-plate, we have OAM with right circularly polarized light. Similarly, so if we have right circular polarized light as an input, so we will have OAM with left circularly polarized light. Now we have our object which is placed at the target site. We have a complex object where AXY represent the amplitude object and BXY represent phase object. So with the help of this system, so we have our output in the vector format because of uh, the input polarized light. So we have the output where edge of the amplitude object has been separated from edge of the phase object. So in our experimental setups, we have used on-end cell where we place on-end on the target, and first we remove the Q plate and we obtain this result. So this is without Q plate. Then we replace the Q plate, we insert back the Q plate, and this is the result we obtain. So this is with Q plate. Now without Q plate, cell wall, which is the amplitude object edge, is visible, but cell nuclei, which is phase object is edge, is not visible. So which is clear from this first image. So the cell nuclei, which is a phase object, is not visible. Now when we use Q plate, the both edge of cell wall and cell nuclei is visible. So which is clear from the second image. So this one is a cell nuclei edge, and these are the cell wall edge. However, the edge of cell nuclei and cell wall has been enhanced equally, so making it difficult to distinguish between these two edge. Now question is how we can distinguish between two edge. The solution could be we could isolate the phase object edge from amplitude object edge. Now from this slide, so let me explain the simulation results that which we have carried out. So this one is our object where we prepared using super Gaussian function. So red indicate the amplitude object edge and yellow indicate the phase object edge. So this one is cross-section intensity distribution for amplitude object and phase object. So we have a laser diode, laser light, which is propagating along z direction. So with the help of this system, where 4F imaging system with Q plate, will give the image where edge of amplitude object and edge of phase object has been dictated. But our main idea is to eliminate the edge of amplitude object. So we want only phase object in order to distinguish between these two edges. Now we have used the tilted laser light, which is traveling on XZ and YZ plane by small angle. So this one is a tilting laser light. Now when this tilted laser light illuminates this object, so we have object with tilted laser light. The color function change in this object is due to tilted laser light. So this object with tilted laser light is seen through optical vortex microscope. So when the incident light is tilted on XZ plane and when angle is positive beta, so small angle positive beta, so we have obtained this image where edge of phase object has been enhanced at the positive gradient and edge has been reduced at the negative gradient. This is because the positive beta angle has been induced in the phase object. Now similarly we have this image when we use negative beta. So when we use negative angle, the edge of this phase object has been enhanced in the negative gradient, whereas the edge has been reduced at the positive gradient. Now if we subtract this positive beta and negative beta, so we get this image where this is basically the partial derivative of phase object with respect to x. Now similarly, when incident light is tilted on YZ plane, we get this image where it is a partial derivative of phase object with respect to y. So if we add these two partial derivative, we get isolated edge of phase object from amplitude object edge. Now here are the simulation result analysis. So this is our object where the radius of amplitude object, that red color, is 12 micrometer, and the radius of that phase object is 4 micrometer. So this one is an ideal edge enhancement of phase object with the help of ideal Q plate, and this one is the edge enhancement of amplitude phase object with normal incident light. where beta is 0 degree, so which is not tilted laser light. Now this one indicates the isolation of edge enhancement of phase object with tilted laser light. So we have used beta equal to 0.2 degree. So if you compare this tilted laser light and not tilted laser light, so in the tilted laser light, the edge has been removed compared to not tilted laser light. Now here we plot the horizontal cross-sectional logarithmic intensity distribution, where red curve indicate the ideal phase object edge, green curve indicate the normal incident light, and purple curve indicate the tilted incident light. Now if you compare, so this one is basically the edge of the amplitude object edge. So if you compare this purple curve with the green curve, so edge has been removed compared to this with the green curve. And the minimum intensity ratio between these two curves was 42 dB. Simulation result analysis continue. So here is the correlation coefficient plotted between ideal phase object edge and numerically isolated phase object edge with our method. So we have increased the amplitude object radius. So amplitude object radius has been wrapped around the phase object. So we increase from 6 micrometer to 20 micrometer, which is shown out here. So at 6 micrometer, so uh, this for this object, so this is the logarithmic horizon cross section distribution for the image for this object. The minimum intensity between the phase object edge and amplitude object edge is 14 dB. Now as we increase the radius of amplitude object, the correlation coefficient improved, and at the 12 micrometer, which I explained in the previous page, so the correlation coefficient was found to be 0.954 correlation coefficient. So finally, the conclusion and future work. So future work, so we will conduct a proof of principle experiment this semester. So thank you one and all.
Yes, thank you very much for your interesting presentation. So let's open the discussion. Do you have any question or comment? Please. Please.
Yeah, this angle beta, what is the optimum value for it, and how do you select it?
Okay, thank you for your question. We have we try to use minimum angle. So we have tried to look at optimized angle. So 0.2 was a better angle, because if you use less than 0.2 degree, so it is not realistic in the practical application. So if you use a very small angle, so it is not realistic. So 0.2 was optimized angle.
Okay, thank you very much. I see.
Do you have any other questions or comments? I have a simple question. So,
okay,
in your simulation analysis, so phase edge information and phase edge patterns and amplitude pattern is completely divided.
Yeah.
So, if you measure, you observe so in the complex edge pattern, so your method is effective or so some or not?
Okay. In the complex object, I couldn't catch up the question properly. If you could.
Yes. So is your method is effective for more complex edge patterns?
Okay, as per the theoretical calculation and the simulation result. So it was the edge could removed not completely, but there is a, minimum edge of amplitude object. We are going to verify through experimental result. So whether it could completely remove the edge of amplitude object edge or not. So as per theoretical calculation and simulation result, the edge was removed.
Thank you. Okay, so thank you for your presentation.
Okay,
So
thank
let's
you,
move
thank you,
next
thank you.
presentation. それでは、本セッションの、4番目の講演で、